Hello everyone, I am Yuki Nanjo from Okayama University, Japan. I would like to give a talk about this research, which is the title Specific Congruence Classes of Integer Parameter for Generating BLS Curves for Fast Pairings. This is the outline of this presentation. First, I will explain the background and motivation of this research. A pairing used for the pairing-based cryptography, which enables several innovative protocols, is typically defined as 2-to-1 map given at equation 1, where D1, D2, and Dt are groups of a prime order R. In practice, D1 and D2 are chosen from rational point subgroups on an elliptic curve with embedding degree k. Besides this, Dt is a multiplicative subgroup of a finite field of order p to k, where p is a prime characteristic. The elliptic curve used for the pairing is often chosen from the families of pairing-friendly elliptic curves, for example, the BLS and BN families. The important fact is that these families have one striking feature in common, that is a prime characteristic p and group order R are fixed by the specific polynomials in terms of an integer parameter x0. In this research, we focus on the BLS family of pairing-friendly elliptic curves for several reasons described from now on. First of all, the BLS family can support the pairing at various security levels, since the family has high flexibility of the choices of embedding degree. With this benefit, the family can also support to optimize the pairing, which is computed by the mirror loop and final exponentiation. As you know that, one can immediately find the shortest mirror loop. In addition to this, according to the recent research in 2020, an efficient algorithm for computing the final exponentiation is also found without effort. Thus, we consider that the BLS family will be regularly adapted for the pairing, even if there is progress in the security analysis in the future. Then, I would like to describe a remaining issue in the BLS family which motivates this research. For the state-of-the-art pairing with the BLS family, it is desired to use subfamilies of the BLS family, which have a nice option such that a tower of extension field with fast arithmetics is available, since the efficiency of the field arithmetics can affect the performance of the pairing. In this presentation, we say that the subfamilies with this option are attractive. The attractive subfamilies can be generated by finding the integer parameter, which specifies the characteristic p and group order R under a necessary and sufficient condition for constructing the favorite tower of extension fields. The condition is typically given by the congruence classes of integer parameter as shown in the equation 2. However, the condition has not been provided except for the case that embedding degree is 24 given by Coste et al. In 2011. Thus, we provide the restriction for generating the attractive BLS subfamilies of the pairing-friendly elliptic curves with more generalized embedding degree, such that k equals 3 to j and 2 to I multiplied by 3, where I and j are arbitrary positive integers. We also give the attractive subfamilies a more option of the immediate determination of the curve equation. In this presentation, we will attach weight to the explanations of the benefits and use of the proposal instead of its derivation. Next, let us move on to the fundamentals. For easier understanding for the proposal, I will carefully explain about the field, elliptic curve, and pairing. Let Q be a prime P or a power P, and let FQ be a field of order Q. A mth extension field of FQ is often constructed by a coordinate ring by a binomial ideal for efficiency reasons in the cryptography. A tower of extension fields is a sequence of these field extensions. An elliptic curve E defined over FQ is given by the equation 5, where A and B are coefficients in FQ satisfying the specific condition. A set of all rational points, including a point at infinity, is known to perform an additive group, which is called a FQ rational point group. For a point P, a point multiplication by a positive integer s can be defined as shown in the equation 6. Let R be a prime factor of the number of FP rational point group, which is given by P plus 1 minus T, where T is an integer called the Frobenius trace. And let K be the minimal integer, where R divides P to K minus 1, and which is called an embedding degree. Then there exists an entire group of points of order R of FPK rational point group, which is called a R torsion subgroup. A pairing requires certain two subgroups D1 and D2 in this R torsion subgroup. A pairing, which is non-degenerate and bilinear, is a map from D1 and D2 to DT, where DT is a multiplicative subgroup of R's root of the identity in FPK. For points P in G1 and Q in G2, the image of the set of the points is given as shown in the equation 8, where FRP is a rational function with a specific divisor. As seen in the definition, the pairing is typically computed by two steps. The first step is computing the value of the rational function FRP evaluated by Q by using an iterative algorithm, which is called the Miller's algorithm. The output of the first step is an element in FPK, and the second step is powering this to the specific exponent in FPK, which is known as the final exponentiation. Please note that this is a very basic pairing explanation, and we have to apply so much optimization for practical using. We also have to mention that the pairing requires a special elliptic curve having small embedding degree k, enough large group order R, and appropriate low value given by the ratio of the size of P and R, which is called a pairing friendly. There are several construction methods of pairing friendly elliptic curves, which are based on an idea of the parameterization of P, R, and T by the polynomials that satisfy the necessary conditions for the pairing. The set of elliptic curves specified by the polynomial parameters is called a family of elliptic curves. As examples of the families of pairing-friendly elliptic curves, the BLS and bin families are well known. That is all of the fundamentals. Now I will describe a main proposal. To describe that, we first review our target BLS family of pairing-friendly elliptic curves. The BLS family has the polynomial parameters given by the equation 9 for generating pairing-friendly elliptic curves with embedding degree k, which is multiple of 3. Since R is given by the polynomial associated with the k cyclotomic polynomial, the BLS family is classified into one of the cyclotomic families. The family also have 4 types of the embedding degrees, where k can be chosen as an arbitrary positive integer of multiple of 3 except for 18. In this work, we especially focus on the BLS family for the specific embedding degree k equals 3 to j and 2 to I multiplied by 3, where I and j are arbitrary positive integers. For the polynomial parameters, let x0 be an integer, making px0 and rx0 being primes. Then, there exists an elliptic curve given as y squared equals x cubic plus p, defined over a prime field with a characteristic px0, such that the group order is given by px0 plus 1 minus tx0, which has a prime divisor rx0, and embedding degree is given by k. This curve is called a BLS curve. As you can see that, it is found that the integer parameter x0 specifies everything. Thus, we consider that the choices of x0 is very important, and one can find some restriction of x0 which is advantageous for the pairing. Indeed, for the embedding degree k equals 3 to j and 2 to I multiplied by 3, we propose to find x0 under the restrictions given by the equation 12 and 13. Once finding x0 under the restrictions, we have the attractive BLS subfamilies with the options, which is the tower of extension fields with one of the best performing arithmetics is available. With this option, we can also immediately determine the equation of the BLS curve. The details of the options are summarized in the tables 1 and 2. As an example, for the case of k equals 3 to j given in the table 1, once finding x0 under the condition of x0 congruence for modulo 6, we can use the tower of extension field defined by using an irreducible binomial alpha to k minus 2. We can also obtain the concrete BLS curve given as y squared equals x cubic plus 16. Please note that these results are based on the mathematical theory and are also proven. The details can be found in the theorems 4 to 7 in the manuscript. Now, I will describe the benefits and remarks of the proposal. Anyway, the proposal gives rise to the attractive BLS subfamilies which result in the first pairing in terms of the field arithmetics, since the proposed restrictions are necessary and sufficient condition for constructing our target tower of extension fields. The proposal also leads to a reduction of the pre-computation of initial setting for the pairing, and gives the reusability of the implementation by the fixed field and curve constructions. The proposal can also provide the same result of the previous work by Costetter for the case that the embedding degree is 24. However, unlike their case, we still cannot give one more option of immediate determination of the twist of the BLS curve. We also mentioned that one of the BLS curves with embedding degree 12, which is the focus of standardization for the pairing-based protocols and is named as BS12381, can be classified into the proposed subfamilies. As proof of that, the integer parameter given in the equation 14, which specifies this curve, satisfies our condition. With this fact, we consider that the proposal will help to find a new curve without changing performance of the pairing and its implementation as far as possible when it comes to updating x0 or k for some security reasons. Finally, conclusion and future work. In this work, we provided the congruence classes of the integer parameter which specifies the BLS family of pairing friendly curves with embedding degree k equals 3 to j and 2 to I multiplied by 3 for arbitrary positive integers I and j. The generated BLS subfamilies have nice options of the field and curve constructions, which are advantageous for the first pairing and its implementation. As one of the future works, we would like to give the attractive subfamilies more option of the determination of the twist. These are the papers referred in this presentation. That is all of my presentation. Thank you for kind attention and watching the video.